Okay, so in the last video I talked about the variance and the standard error of any beta coefficient, and I showed you how this standard error is calculated manually. And in this video I'm going to keep talking about the same example where we are interested in math score and the percent of household those are single. But instead of using one variable, I'm going to use three variables as explanatory variable of somebody's math performance, and I'm going to include median household income and whether somebody is eligible for a free lunch program in the school. I'm going to include these variables and then run math scores on this, and essentially the goal is to calculate the standard error of percent of single household, which is our variable of interest. The first thing I want to do is I'm gonna run the full regression model and note down the standard errors of the regression output. So this is 11.7. So we have our first number here, and the next thing I'm going to do is I'm going to save this sigma as SER, that is the standard error of regression, because later on I'm going to use this to calculate the standard error of beta j in R instead of writing down everything here. So I'm going to save this SER and see it is 11.69, which is about 11.7. The next thing I'm going to do is I'm going to calculate R squared running our variable of interest single parents on the other two variables, that is the median income and whether somebody is eligible for this program. I'm gonna pass summary command to get the summary of it, and then I'm extracting R squared of this regression and saving it as R squared of single households. So this is 0.82, and from this I'm going to use this formula to calculate variance inflation function. As I showed you earlier, it is 1 over 1 minus R squared. I'm going to save this variance inflation function as VIF single percent. As you can see, the variance inflation function is 5.74, which is not that high, and based on the threshold that we saw earlier, we said that a value of VIF which is above 10, it shows the presence of multicollinearity between these variables, but seems like this value is below that threshold. The other way you can calculate variance inflation function of all the variables in the model is to use this library car, and then using this function VIF and then passing a regression model to this VIF, and what this function will do, it will calculate variance inflation function of all the variables in the model. As you can see here, PCT single, it is 5.74. It is the same as we calculated manually, and in addition to that, the inflation function of L median income, it is 4.11, and variance inflation function of free is 3.188. So if we regress L median income on other two variables and get the R squared and pass it to this formula, you will get the other variance inflation functions. Okay, so that's how you calculate the variance inflation functions. 5.7. The next thing I'm going to do, I'm going to calculate SST. As I showed you earlier, SST, that is the total sum of squares of our main variable of interest, which is PCT single. Here is we can use standard deviation and multiply it by n-1 to get xj minus x bar. That is how much of the variation is in this variable relative to the mean, and I'm going to save this number as SST percent. We can have a look at this value right here, SST percent, which is 176.57. Okay, so instead we need to take the square root of this number because we are calculating the standard error instead of the variance of beta j. So if we divide this by this and multiply it by the variance inflation function, we'll get 0.15. So that's the standard error of PCT single. I'm going to use this formula. So what I'm doing here is I'm saving the number of observations here, n, and then I'm calculating SST, which is exactly what I did in my earlier example. It's exactly the same thing. I'm multiplying the standard deviation by the square root of n-1 to get this term, and then I'm plugging in everything in the formula, this whole formula, and getting the standard error, which is 0.158, which is exactly equal to this. So what we can do here is we can look at our original equation and see here what is the standard error of PCT single. It is 0.158, and we can compare it with our earlier model. In the earlier model, with only one variable in the model, it was 0.07, and now it has increased to 0.15. Seems like including these other two variables, it's increasing the variance of our variable of interest. So what is happening with the coefficient value? The coefficient value is actually less than the actual value. So seems like in our simple model, there was an upward bias in our estimated slope coefficient, but when we include other variables in the model, it is bringing this coefficient of interest to a lower value. But on the other hand, the variance is increasing, and this is exactly what we saw in some of the previous videos, that standard errors or the variance of a simple model, it is always less than the variance of a multiple linear regression model that is controlling for other variables. It may increase the variance of your variable of interest. So now the question is, since these variables, they are increasing the variance of our variable of interest, should we exclude any of these two variables from the model? The answer is no. Although the correlation between these variables is very high, the sample correlation between median income and this variable free, it is about 0.74. And this is expected because as the median income increases, the eligibility to enroll in a free lunch program decreases. The other reason we need not to drop these variables from the model is because multicollinearity seems like not a huge issue in this model, as we saw in the variance inflation function that the VAF values, they are less than the threshold value. So it's giving us an idea about whether these variables are highly correlated with each other or not. It is clear that we should not drop both median income and free variables from the model. So we should go with the full model rather than regressing the model only on our variable of interest. Alright, so that was an example of variance or standard error, and essentially you don't have to calculate everything by hand because R is already providing you this standard error, and the importance of this standard error will be more clear to you when we will talk about the statistical significance of these variables in the next chapter. Alright, I'll see you in the next video.